Hi, my name is Qingqing Tan. So I'll be presenting my project, the stacked ensemble modeling for immune recovery prediction in HIV patients. HIV progressively weakens the immune system by destroying CD4 T cells. So CD4 count is one of the clearest indicators of disease progression and treatment effectiveness. This project has two levels of business understanding. At the project level, the task is to build a model that predicts CD4 net change after 20 weeks of therapy using patient demographics and clinical variables. And at the clinical level, predicting CD4 improvement supports the broader goal of identifying which patients may benefit from certain therapies. In real settings, knowing who will respond to treatment helps clinicians tailor antiretroviral strategies. The dataset comes from ACTG study 175, a trial comparing monotherapy versus combination therapy in HIV-infected adults. CD4 counts were measured at baseline, called CD40, and again at week 20, called CD420. Biologically, CD4 counts can range from 0 to around 100 and 600, around 1,600. Values below 200 indicates AIDS, and although rare, values near zero do occur in severely immunocompromised patients. That explains why dataset contains CD4 values below 200, despite the study description highlighting the 200 to 500 range. CD8 counts range from 0 to over 1,500 and reflect immune activation or suppression. These variables help describe patient immune status at baseline. The dataset contains 2,139 observations and 23 variables, consisting mostly of binary clinical indicators. There are no missing values except for unrealistic zeros in the Karnofsky score, which represent functional health and ranges from 0 to 100. Since 0 indicates death and patients cannot be dead at the recruitment, these values were imputed. 8 features contain outliers, but except for the 0 Karnofsky scores, all outliers were clinically plausible and therefore retained. Because CD4 and CD8 are both T cell subsets, I explored whether they show any meaningful relationship. The scatter plot shows a wide diffuse cloud with only a weak upward trend, indicating almost no linear relationship. This is typical for immune data where many biological factors influence cell counts simultaneously. This early exploration suggests that strictly linear models may struggle because feature relationships are weak and highly variable. When comparing the distributions, CD4 is relatively symmetric with moderate variability. CD8, however, has a large interquartile range and a heavy right-skewed pattern. CD8 T cells can expand rapidly during immune activation, so a long right tail is biologically expected. These non-normal and heterogeneous distribution further support using models that can handle long linear structure. I framed the task as a three-class classification rather than regression. Small numeric fluctuations in CD4 may not be clinically meaningful, but distinct thresholds of improvement are. Classification reduces noise, increases interpretability, and allows a wider range of modeling techniques. I trained these three base learners. One is a random forest homogeneous ensemble, a bagged decision tree ensemble, and then a multinomial logistic regression model. I think each one captures different structural patterns in the data. I engineered the target variable as CD4 net change, which is CD420 minus CD40, because this directly measures treatment effect. Then I converted the net change into three clinically meaningful improvement. improvement levels using NIH thresholds. I removed post-treatment variables such as CD420, CD820, and the infected status to avoid the data leakage. Categorical features were converted to factors for tree-based models, and numeric features were standardized only for multinomial logistic regression. Karnofsky's score was imputed using a decision tree because it handles non-linear relationships and mixed data types better than KNN and linear regression. Imputation of Karnofsky score, I excluded the non-predictive features, and then I imputed the zero values with NAs, and then I split the data into complete and incomplete data. So the incomplete data consists of all the observations with the NA value, and then I used decision tree method to train the model, and then I used the model to impute the Karnofsky score. So random forest was trained with five-fold cross-validation, upsampling, and M-tree tuning. Scaling was unnecessary because trees handle mixed data types and non-linearities. After testing all three rebalancing methods, the upsampling with k-fold cross-validation and M-tree tuning was selected for the final heterogeneous ensemble. So the reason I chose this specific model is because this model performed the best on the minority class, which is the moderate improvement class. I know that there's class imbalance in the data, even though I used upsampling and SMOTE to decrease the effect of the class imbalance. All the models have very imbalanced performance across all the classes. So this is the code I have for building this specific model. I use upsampling manually, and then I use k-fold cross-validation, and then I use the tuned number of variables considered at each split. So I explored both a simple bagged decision tree model and a complexity parameter tuned version. The tuned model performed better overall because complexity parameter tuning stabilized the trees, preventing overfitting and improved generalization. So the final model I chose achieved a balanced performance across classes and performed reasonably well for both moderate and strong improvement. Those two classes are both clinically meaningful outcomes. For the decision tree I selected, I first built a fully grown tree, and then I plot the complexity parameter graph here, and then I picked the best complexity parameter and for training the bagged decision tree model with upsampling. Multinomial logistic regression cannot be bagged effectively due to categorical imbalance, which causes complete separation in bootstrap samples. So I trained a single model with upsampling and decay tuning. The model I selected for the final ensemble achieved the most balanced F1 score performance across all classes, especially for the moderate improvement category, though its overall accuracy was lower than the tree-based models. It also performed comparably to all other models on strong improvement class. Binomial logistic regression that uses upsampling and decay tuning. So here I create the F1 score summary function for multi-class, and then I used five-fold cross-validation, and then I used the F1 score as the performance metric, and then I trained a model. So this is the overview of all the base learners I selected for building the heterogeneous stacked ensemble. This table compares all the base learners. Random forest has the highest accuracy, but performs the worst on the moderate improvement class. And then multinomial logistic regression has the most balanced F1 score and performs best on the moderate class. And then the bagged back decision tree provides a stable and moderate performance across all classes, including the strong improvement class. Since the moderate and the strong improvement represent the true clinical benefit of the therapy, models that better detect these groups are clinically preferable, even if accuracy is slightly lower. So weights were assigned based on each model's contribution. Multinomial regression received the highest weight due to balanced class performance. And then the homogeneous decision tree model received moderate weight because it performs well on both improvement classes. And the random forest received the lowest weight because it mostly learns the dominant class. The final ensemble achieved more balanced F1 score across all three classes, including an improvement in detecting the strong improvement. Final heterogeneous ensemble. I first built a function that takes 5 arguments. So it takes three different models, probability, and then weights, and then the class levels. And then I apply the function, and then I extract the predictions for model evaluation. Support vector machine was initially considered, but performed poorly. The radial basis function kernel also showed consistent poor performance, um, and it failed to capture structure in sparse, mostly binary dataset. The linear kernel suffered from convergence issues because the classes are not linearly separable. This demonstrated the importance of empirical model selection. Some black box models look promising theoretically, but are unsuitable for the dataset's characteristics. I also explored bagging multinomial logistic regression, but many bootstrap samples lost minority predictor levels entirely. This caused complete separation and unstable convergence. This reinforced a key lesson, which is that resampling-based ensemble methods do not work well with categorical models when predictors are extremely imbalanced. In summary, each model contributes different strength, and random forest captures complex nonlinear patterns. Bagged decision tree provides stable threshold-based decisions. Multinomial regression captures linear separability across classes. By combining them into a heterogeneous stacked ensemble, I achieved the most balanced and clinically meaningful performance across CD4 improvement levels. And these are the references.